Good evening, everyone. Welcome to another tutorial of this applied thermodynamics course. I am Thananka Zutia, a PhD student at Center for Atmospheric and Oceanic Sciences, and I'll wait for a couple of minutes for others to join. In the meanwhile, I'll share my screen. Thank you. So I hope the screen is visible. Okay, so last class I left a couple of questions to solve. I'll solve them first, and then we'll move on to solving these weeks, whatever you have learned in the theoretical classes, those solutions. So we'll wait for 1 more minute and then we'll start to solve the questions. Okay, so let us start today's class. I hope people will join if they are not watching the cricket match. Okay, so uh, calculate the minimum volume of air that is required to burn 1 kg of coil having the following composition by weight. It is having carbon 72.4%, it's having hydrogen 5.3%, nitrogen 1.81%, oxygen 8.5%, moisture 7.2%, sulfur 0.9%, and ash 3.9%. Okay, and you have to assume the NTP conditions, that it pressure is 1 atmosphere and temperature is 293 Kelvin. Okay, so you are given a coil, okay, and that coil has some composition of say carbon whatever, and then uh, you have to identify what is the minimum volume of air. You have to calculate the volume of air that is required for the combustion of these products. Okay, so suppose if this is my coil, okay, so it contains carbon 72.4%, hydrogen 5.3%, nitrogen 1.81%, oxygen 8.5%, moisture 7.2%, sulfur 0.9%, and ash as 3.9%. Okay, so out of this is the composition of the coil. So if you want to oxidize this coil, or if you want to burn this coil, you have to pick out which are the components of the coil that are eligible for burning. That means that can undergo oxidation process, or that can undergo combustion process. So carbon, this is one. Okay, hydrogen, this is one. Nitrogen, we all know that the mixture of that nitrogen is basically, it's an unreactive component, so it will not go reaction. Oxygen is already there, moisture is already oxidized, and one more part, that is sulfur. So these three products that is present here, they will undergo oxidation. Okay, so now you have to calculate what is the amount of air basically required to undergo for the combustion, because only these are the products which can undergo combustion. The rest, they will not go combustion, either they are already combusted products or they are unreactive products. Okay, fine. So again, the composition of this is given in percentage, so we don't know what is the actual composition, so we will just assume that let mass of coil is equal to 1 kg. Okay, so we'll assume that the mass of the coil is equals to 1 kg. Okay, so therefore mass of the components are carbon 0.724 kg, okay, then hydrogen 0.053 kg, okay, then nitrogen 0.0181 kg, then oxygen 0.085 kg, okay, and then moisture 0.072 kg, okay, moisture, sulfur 0.009 kg, and ash you will have 0.039 kg, okay. Now we know that combustion or say burning takes place in presence of oxygen. So what we have to do, we need to first calculate the amount of oxygen required to undergo the given combustion reaction, okay. So our first motive will be to calculate the amount of oxygen that is required for the combustion, okay. Now combustion of carbon, okay. So combustion of carbon, the reaction we all know, C plus O2 gives CO2, and remember we are talking about complete combustion, so we will not talk about carbon monoxide being formed, okay. So many of you might think like C plus O can also be forming carbon monoxide, but here we are talking about complete combustion, and that is why we are only considering the carbon dioxide produced. So 12 and this is 32, so 1 it will be 32 by 12, and so how many kg of carbon we have? It's 0.724, and that will be equal to 32 divided by 12 into 0.724, that is equal to 32 into 0.724 by 12, okay. So you'll get this 1.93 kg, 1.93 kg, okay. Fine. Next, combustion of hydrogen, okay. So the combustion reaction of hydrogen is H2 plus O2, this will produce H2O, and if we balance it, 2 of oxygen, and then this will be, okay. So this will be 4, this will be 32, 1, it will be 32 divided by 4, and so what kg of hydrogen is there? 0.053, 0.053, that will be equal to 32 by 4 into 0.053 kg, okay. So that is 0.424 kg, okay. To burn the amount of hydrogen that is present, this much amount of oxygen we require, okay. Again combustion of sulfur. Okay, so that will be again S plus O2, this gives SO2. Okay, this is balanced already, so this will be 32, this will be 32, so 1 will be equal to 32 divided by 32. And what is the amount of sulfur is present? 0.009, so 0.009, that is 32 divided by 32 into 0.009 kg, and that is equal to your 0.009 kg. Okay, fine. So now we have calculated the amount of oxygen that is required for combustion of the different combustible products that is present in the coil. So therefore total oxygen required to burn 1 kg of coal is equal to what? 1.93 plus 0.424, okay, plus 0.009 kg. Okay, so if you add this, you will get it as 2.363 kg. Okay, so this much amount of oxygen is required to undergo combustion of the coil having the given compositions. Okay, now there is already oxygen present. Okay, now amount of oxygen already present is equal to what? 0.085 kg. 0.085 kg. Okay, so therefore additional amount, or actually you have to write that the actual amount of oxygen, therefore actual amount of oxygen required for combustion will be what? Combustion will be 2.363 minus 0.085 kg. Okay, and that will be equal to 0.363 minus 0.085, 2.278 kg. Okay, 2.278 kg. Okay, so this much amount of oxygen is now actually required, because there's some amount of oxygen is already present, so we have subtracted it. Okay, fine. Now we know what we know. Air contains 23% oxygen by weight. Okay, because remember we have to calculate the volume of air, so from this composition of oxygen we will actually have a link to the amount of air that is required. So what does this mean? That is 100 kg of air contains 23 kg of oxygen. Okay, in other case, now the thing is very clear. 23 kg of oxygen is equal to, actually I'm writing it's equal, but it is contained in 100 kg of air. Okay, now 1 kg of oxygen will be equivalent to 100 by 23 kg of air. Now what is the kg of oxygen that is actually required is 2.278 kg of oxygen is equal to 100 by 23 into 2.278 kg of air. Okay, so we have now got the mass of 100 into 2.278 by 23. Okay, so you got it as 9.90 kg of air. So now for the complete combustion of the coil of the given specifications, we have got the mass of the air required. But remember, our question is the volume of this one required. So for that, we have the ideal gas equations now. From ideal gas equation, what we can write? PV is equal to MRT. Okay, so given is what? P is equal to what? P is equal to 1 atmosphere. 1 atmosphere. Okay, so that means 1.013 into 10 raised to the power 5 Pascal. Okay, this P is given. What is the value of T that is given? 293 Kelvin. Okay, so T is equals to 293 Kelvin is given, and we know the value of this one R is already as 0.287 kilojoule per kg Kelvin. Okay, so we know these things, and also we know the mass of the air, that is 9.90. So we put all this implies P. So I will express this in case of kilopascal. 1.013 into 10 to the power 2. Okay, that is kilopascal. And what is the volume V that is already required? And we have already the mass 9.90, R 0.287, and the temperature is 293. And from here, volume V is 9.90 into 0.287 into 293 divided by 1.013 into 10 square meter cube. Okay, 9.90 into 0.287 into 293 divided by 1.013 into 10 square. Okay, so you will get your answer as 8.218 meter cube. Okay, so therefore the minimum volume of air required to burn 1 kg, not actually 1 kg, you can give the to burn coil any amount of kg, because just in terms of percentage only we are expressing, to burn coil of given composition is equal to 8.218 meter cube. Okay, it's very simple. In the coil, not all the products are present are combustible, so we are first calculating the amount of oxygen that is required to undergo combustion for the different combustible products, and from that we know that a relationship between the mass of oxygen, actually the ratio of the mass of oxygen and air, we know this relation, and from there we have calculated the mass of the air first, and from that mass of the air we have calculated the volume of the air first. Okay, so now the next question: consider a fuel with an equimolar mixture of propane and natural gas. Determine the stoichiometric air-fuel ratio on a molecular basis and molar air-fuel ratio for combustion at an equivalence ratio of 0.8. Okay, Fine. So how will we solve this? Theoretical air required for complete combustion of propane. Okay, so that will be C3H8 plus A into O2 plus 3.76 into N2. This will give B CO2 plus C H2O plus D N2. Okay, so now performing the balance, C will be equal to what? Carbon balance if you do, then B will be equal to C. You will get, if you balance hydrogen, you will get 2C is equal to 8, so this implies C is equals to 4. And if you balance oxygen, you will get 2A is equal to 2B plus C. Okay, so that means what? 2 into B, that is 6 plus 4, so this implies A will be equal to 5. And if you balance nitrogen, what you will get exactly? A into 3.76 is equals to D, so it implies D is equals to 5 into 3.76. okay, (18.8). Fine. So we have got this. We'll write the combustion reaction later on. Also, theoretical air required for complete combustion of methane. Okay, so here we'll just put, in place of propane we'll just methane plus A prime times O2 plus 3.76 N2. This gives B prime times CO2 plus C prime times H2O plus D prime times N2. Once again, if we do carbon balance, we will get B prime is equals to 1. If we do hydrogen balance, we will get 4 is equals to 2 C prime, so this gives C prime is equals to 2. We'll do oxygen balance, we'll get 2A prime is equals to 2B prime plus C prime. Okay, so 2B prime plus C prime is equals to what? 2 into B prime is 2 plus 2, that is 4. Okay, so this implies A prime is equals to 2. And if we do nitrogen balance, we will get A prime into 3.76 is equals to D prime. So what is A prime? 2 into 3.76, that is 7.52. Okay, so now we can write, therefore theoretical air complete combustion reactions are C3H8 now plus A, in place of A we know the value of A now, plus 5 times O2 plus 3.76 N2 gives what is B? 3 CO2 plus 4 H2O, okay, plus 18.8 N2, and for methane CH4 plus 2 O2 plus 3.76 N2, okay, gives CO2 B is equals to 1, B prime is equals to 1 plus 2 H2O plus 7.52 into N2. Okay, fine. So we have got the theoretical complete combustion reactions for both methane and propane. Now, number of moles of oxygen required to burn 1 kilomole of C3H8. So number of moles of oxygen that is required to burn 1 kilomole of propane is equal to what? 5 kilomole. Correct, no? From the reaction 1. And also number of moles of oxygen required to burn 1 kilomole of methane is equal to what? 2 kilomole. Okay, now this is the component, that is for complete combustion this much kilomoles of are required, okay, for each of the individual component. Now it is telling us that according to question, equimolar mixture of methane and propane is to be used. Okay, that means the number of moles of ethane and propane should be same. So therefore let us consider the number of moles of fuel is equal to 1 kilomole. So I have considered the number of moles of the fuel as 1 kilomole. Therefore number of moles of propane will be equal to what? 0.5, and also number of moles of methane is also equal to 0.5 kilomole. Okay, so since they are equimolar, so we have taken the total number of moles just like the previous questions. Okay, so therefore number of moles of oxygen, number of moles of oxygen required for complete combustion of the fuel is equal to what? See, 1 mole you require 5, yes or no? For 1 mole of methane you require 5 kilomole, but now you have 0.5, so it will be 0.5 into 5 plus 0.5 into 2 kilomole. Okay, so that means 0.5 into 5 is 2.5 plus 1 kilomole, and that is 3.5 kilomoles. So 3.5 kilomoles of oxygen is required to completely burn this given amount of fuel, which contains equal number of moles of propane and methane. Okay, now we should not calculate the number of moles, we have to actually calculate the air fuel ratio. So now we will calculate the number of moles of air. The number of moles of fuel is already 1, so the number of moles of air whatever you will get, that will be actually your answer for your air fuel ratio. Okay, now since air contains 21% oxygen by volume, okay, so therefore volume of oxygen divided by volume of air is actually equal to what? 0.21. Okay, now if you write PVA is equal to NART, okay, and PV is equal to NRT, okay, T where A stands for any substance A, and T stands for total. Okay, now if you take this ratio, PVA by PVT is equal to NART divided by NTRT. Okay, so what actually it says that VA divided by VT is equals to NA divided by NT. What is VA divided by VT? That is the ratio of volume of a particular component divided by total component, is nothing but the volume fraction of A is nothing but is equals to the mole fraction of A. Okay, so this means volume fraction of A is equal to mole fraction of A. Okay, so therefore now we can also write NO2 divided by N of air, that is number of moles of oxygen divided by number of moles of air, is equal to 0.21. Okay, so we already know the number of moles of oxygen, that is 3.5 kilomole. So number of moles of air, and that is equals to 0.21, and from here number of moles of air is equals to what? 3.5 divided by 0.21 kilomole. Okay, 3.5 divided by 0.21, this is 16.67 kilomole. Okay, so now you got the number of moles. Therefore air fuel ratio on molar basis is equals to what? Number of moles of air divided by number of moles of fuel. Number of moles of air you have got 16.67, and number of moles you have taken as 1 kilomole. Okay, so that is 16.67. Is it clear? So this is the first part. This is how we are doing. Okay, the stoichiometric air fuel ratio on a molar basis. Now second is equivalence ratio. We need to calculate the molar air fuel ratio, that is actual air fuel ratio. Okay, actual air fuel ratio. Okay, so given equivalence ratio that is phi is equal to what? 0.8. Okay, so therefore, and also we know that phi is equals to air fuel ratio stoichiometric divided by air fuel ratio actual. Okay, so this phi 0.8, we have already calculated 16.67 as the stoichiometric air fuel ratio, and now we need to calculate the actual air fuel ratio here, and from here air fuel ratio actual will be basically equal to 16.67 divided by 0.8. Okay, .84. Clear? Okay, So let us go to the next question then. A spark ignited engine operating at 2500 rpm has a combustion duration of 60-degree crank angle. If the spark plug is centrally located on the cylinder head and the cylinder bore is 80 mm, estimate the average flame velocity for complete combustion. Okay, so these are from here on. Now we are starting the sums that are related to this week's questions. Okay, so given n is equal to 2500 rpm. Okay, theta that is what your crank angle is given as 60 degree. Okay, and bore diameter is given to you as 80 mm. Okay, and the cylinder is centrally, sorry, the spark plug is located on the cylinder head itself only. Okay, so there is no offset there. Okay, so you have to estimate the flame velocity. Okay, so flame velocity is equal to what? Distance traveled by flame, distance traveled by flame to the time required by the flame. Okay, so these are the things. Now distance is equals to b by 2. Okay, since there is no offset, so it will not go any heading here, so that will be 80 divided by 2, that is 40 mm. Okay, and I can write this one as 40 by 1000 meter. Okay, now we know one rotation or one revolution, basically you have to tell number of revolutions per second. So one revolution of crank is equals to 360 degree. Okay, now therefore number of revolutions completed in 60 degree crank angle. Why? Because 60 degree is the combustion duration, that means the flame whatever it starts, that combustion plus. Okay, so that is 60 degree crank angle, and so this will be equal to your 60 by 363 60 revolutions. Yes or no? 60 by 360 revolutions. Therefore time required T is equals to what? Number of revolutions by number of revolutions per unit time. Okay, so what is the number of revolutions? 60 by 360. And what is the RPM? 2500 divided by 60. Okay, so this will be revolutions and this will be revolutions per second. Okay, this one 60 by 360 into 60 by 2500. Okay, seconds. Four into 10 to the power minus 3 seconds. Okay, so this is the time required. So therefore flame velocity is equal to what? Distance divided by time. Okay, distance is 40 divided by 1000 and time is 4 into 10 raised to the power minus 3, so that will be meters per second. Okay, if you do these calculations you will get this one. 10 meter per second. Okay, clear? Okay, so moving on to the next question then. An automobile has a 3.2 liter 5 cylinders 4 stroke cycle diesel engine operating at 2400 rpm. Fuel injection occurs from 20 degree before BDC to 5 degree after TDC. The engine has a volumetric efficiency of 0.95 and operates with fuel equivalence ratio of 0.80. Light diesel fuel is used for this operation, and the engine has a compression ratio of 18:1, and the air operates on air standard dual cycle. At the same speed, combustion starts at 7 degree before TDC and lasts for 42 degree of engine rotation. The ratio of the connecting rod to the crank offset is 3.8. Determine the injection duration, the injector mass flow rate, and the ignition delay. Okay. Given volume V is equal to 3.2 liter. Okay. N is equal to 2400 revolutions per minute. Okay. Fuel injection (20° before TDC to 5° after TDC. Okay, and volumetric efficiency is given as 0.95. Equivalence ratio is given as 0.80, and density of air, we know it. Density of air is equals to 1.81 kg per meter cube. Okay, these two things you have to know. And air fuel ratio, stoichiometric, is equals to 14.5. Okay, these two parameters you need to know. Okay, now this is a 3.2 liter 5 cylinders. Okay, there are 5 cylinders, so whatever volume is given, this volume is for the total number of 5 cylinders. So first of all, we will do this by calculating the displacement volume of one cylinder. Okay, so that will be Vd, which will be equal to V by 5, that is 3.2 divided by 5. Okay, liter, and this one you can express this in meter cube, so this will be 0.0064 meter cube. Okay, now what is volumetric efficiency? Eta volumetric efficiency will be basically equal to mass of the air divided by density of the air into Vd. Okay, so volumetric efficiency we know 0.95. Okay, mass of the air we need to calculate. Density of air is 1.81 and Vd is 0.00064. Okay, so from here, mass of the air 0.95 into 81 into 0.00064. So you'll get this one as 1.1 into 10 raised to the power minus 3 kg. Okay, so this is your mass of the air. Now phi is equal to air fuel ratio stoichiometric divided by air fuel ratio actual. Okay, so what is phi? Phi is 0.80. Air fuel ratio stoichiometric is 14.5, and air fuel ratio actually is what? Mass of the air divided by mass of the fuel. So from here, mass of the air divided by mass of the fuel is nothing but 14.5 divided by 0.80. So from here, mass of the fuel will be equal to mass of air into 0.80 divided by 14.5. What is mass of air? 1.1 into 10 to the power minus 3 into 0.80 divided by 14.5 kg. Okay, 0.1 into 10 to the power minus 3 into 0.80 divided by 14.5. Okay, so this is 6.06 into 10 to the power minus 5 kg. Okay, so this is your mass of the fuel. Now we have to calculate injection duration first. Okay, so injection duration. Okay, since fuel injection occurs 20 degree before TDC to 5 degree after TDC. Okay, so that means if this is your TDC, so from 20 degree before TDC to 5 degree after TDC, this happens. So therefore injection duration, injection angle basically will be equal to what? 20 plus 5 is equals to 25 degree. Okay, so 25 degree of the crank rotation happens during the injection process. Okay, fuel injection process. Fine, so this thing only we have to find in terms of duration now similarly, since so number of revolutions completed, therefore number of revolutions completed in 25 degree crank rotation will be equal to what? 25 by 360 revolutions. Why? Because one revolution is equals to 360 degree. Okay, therefore duration of injection is equal to what? Number of revolutions divided by number of revolutions per unit time. Okay, that means your RPM. So the number of revolutions we have already calculated for the injection duration is this one. This is the number of revolutions they have completed, and your RPM is given as 2400, and if I divide it by 60, so this will be revolutions per second. So this will go and you will get your answer in seconds. Okay, 25 into 60 divided by 360 into 2400. So this is 1.736 into 10 to the power minus 3 seconds. Okay, so this is your injection duration. Fine, next is your injector mass flow rate. Second, we have to calculate injector mass flow rate. Since the injector injects fuel, okay, so and we know that time of injection is we already have. So whatever is the mass flow rate of the fuel is basically the mass flow rate of injector. Okay, so basically m dot f is equals to what? Mf divided by T. Okay, so that is what is the mass of the fuel 6.06 into 10 to the power minus 5, 6.06 into 10 to the power minus 5 kg, and this duration is 1.736 into 10 to the power minus 3 seconds. Okay, 6.06 into 10 to the power minus 5 divided by 1.736 into 10 to the power minus 3. Okay, so 0.034 0.035 kg per second. So this is your injector mass flow rate. Okay, this is your injector mass flow rate. Next is your ignition delay. Ignition delay. Okay, so as soon as your fuel is injected, the let me repeat once again what the question says. Okay, combustion starts at 7 degree before TDC. Okay, but your fuel injection occurs 20 degree before fuel injection occurs 20 degree before TDC. Okay, so let me write once again. Fuel injection occurs 20 degree before TDC. Okay, but combustion starts 7 degree before TDC. Okay, so combustion starts 7 degree before TDC, but fuel injection occurs 20 degree before TDC. So if this is your TDC, okay, so this is the place where fuel is injected. Okay, so that is 20 degree, but your combustion starts here, that is 7 degree. This is combustion. Okay, so that means there is a delay. So till here the fuel is present at this one, but it is not starting to ignite until it goes to 7 degree before TDC. So therefore your ignition delay is equal to what? 20 minus 7, that is 13 degree. Now this ignition delay in seconds we can write. Ignition delay in seconds, that will be equal to what? Similar to that, 13 by 360 revolutions it will make if the crank angle is 13 degree and the RPM is 2400 divided by 60 revolutions per seconds. Okay, so that is 9.027 into 10 to the power minus 4 seconds. Okay, clear? Okay, so let us go to the next question then. A 3 liter 5 cylinder 4 stroke SI engine with a volumetric efficiency of 0.82 operates at 3000 rpm. Bore and stroke are related as S equals to 1.08 B. The engine uses gasoline with equivalence ratio of 0.9. At a certain point in the engine cycle, the gas temperature in the combustion chamber is Tg is equals to 2100 degrees Celsius, and the cylinder wall temperature is Tw is equals to 190 degrees Celsius. Calculate the approximate convection heat transfer, that is rate to the cylinder wall at this instant. Okay, so if you want to see what actually is happening here, if this gas is at temperature Tg, and as it comes down, okay, so then there will be a linear decrease this Tg. So this is basically your inner side, and this is basically your outer side. Okay, and this is your cylinder wall with a thickness of delta x. Okay, but now here the different types of heat transfer processes are taking place. So from Tg to Tw, the convective heat transfer is taking place. So that part only we need to calculate here. They are not telling us to calculate any radiation heat transfer or your conductive heat transfer. They are only telling us that calculate the convective heat transfer. Okay, so what is the given? Given 3 liter 5 cylinder 4 stroke SI engine. Okay, so and again volumetric efficiency is given to you as 82%. Okay, RPM is given as 3000. Okay, and stroke and bore are related as 1.08 B. Okay, and Tg is equals to 2100 degrees Celsius, and Tw is equal to 190 degree Celsius. Okay, equivalence ratio phi is given as 0.9. Okay, so we know convective heat transfer per unit area is equal to what? Q convection, and that is equal to H into Tg minus Tw, where H is the heat transfer coefficient. Okay, so from basic heat transfer coefficient. Okay, so from basic heat transfer, this is basically the formula, working formula. So now the entire problem, because we already have Tg and Tw, the entire problem now comes how you calculate H. Okay, so this H calculation we have to go by the empirical relations from now we know Nusselt number is equals to H into B divided by kg. Okay, for gases, Nusselt. Okay, and this can also be written as C1 RE times C2, where Nu is nothing but Nusselt number. Okay, Hg heat transfer coefficient, Hg is heat transfer coefficient. Okay, B is bore. Okay, C1 is constant, and that is equal to your 0.035. C2 is again another constant, and that is equal to your 0.8. Okay, Kg is the conductivity of that gas, that is 0.09 watt per meter into Kelvin here in this case. Fine. And Re is the Reynolds number. Now this Reynolds number again can be calculated using this formula, ma dot plus mf dot divided by ap into mu g into p. Okay, where ma dot mass flow rate of air, mf dot mass flow rate of fuel, okay, then ap is area of piston, okay, ap is area of piston, and mu g is the what you call viscosity of the gas, and that is equal to, in this case it is 5.2 into 10 to the power minus 5 kg per meter into second. Okay, and b is as usual is the bore. Okay, so now you have to calculate the Nusselt number from C1. So basically you have to calculate the Reynolds number. For calculating the Reynolds number, you require B, you require MA, you require MF, you require AP. Okay, so first of all we will calculate B. How? VD is pi by 4 into B square into S. Okay, and again VD is also equals to 3 by 5 liter, that is 0.6 liter. So from here 0.6 into 10 to the power minus 3, that will be equal to pi by 4 B square into 1.08 B. Okay, so that means B cube is equals to 4 into 0.6 into 10 to the power minus 3 divided by pi into 1.08. So from here B into 0.6 into 10 to the power minus 3 divided by pi into 1.08, okay, to the power 1 by 3. So that is 0.089 meter. 0.089 meter. Okay, so this is your bore diameter. Therefore my area of the piston will be now pi by 4 times B square. Okay, that is pi by 4 times 0.089 whole square. Okay, (6.22) into 10 to the power minus 3 meter square. Okay, so area of the piston is done. Area of the piston done, bore done. Now we have to calculate mass flow rate of air. So mass flow rate of air will be equal to what? Volumetric efficiency into A into VD into N divided by small n. Okay, so volumetric efficiency is 0.82, density of air 1.18, we already know this, 1.18. okay, and VD, we have calculated the VD as 0.6 into 10 to the power minus 3. Okay, and your N is 3000. Okay, revolutions per minute, so I can divide this as seconds, so this will be revolutions per second, and since this is a 4-stroke engine, so n will be, small n will be equal to 2. So from here your mass flow rate of air will be known, 0.82 to 1.18 into 0.6 into 10 to the power minus 3 into 3000 divided by 120. Okay, so your mass flow rate of air is equal to 0.014 kg per second. Okay, so this is your mass flow rate of air. Now equivalence ratio is equals to what? Air fuel ratio stoichiometric divided by air fuel ratio actual. Okay, your equivalence ratio is given as 0.9. Air fuel ratio stoichiometric, I already told you that it will be 14.5, and this is ma dot by mf dot. Okay, so from here mf dot is equals to what? 0.9 into ma dot divided by 14.5. so it's 0.9, ma dot is 0.014 divided by 14.5 kg per second. So this is mf dot, which is equals to 8.68 into 10 to the power minus 4 kg per second. Okay, so you got mf dot, you got ma dot, you got b, you got ap, and you have mu g. So therefore you can calculate the Reynolds number now. Therefore Reynolds number is equals to what? ma dot plus mf dot times b divided by ap into mu g. Okay, so ma dot is 0.014 plus mf dot 8.68 into 10 to the power minus 4. Okay, into b is what? 0.089 okay, and ap is equal to 6.22 into 10 to the power minus 3. Okay, and mu g is equal to 5.2 into 10 to the power 5. 5.2 5.2 into 10 to the power minus 5. Okay, so this is 4091.18. Okay, so you got a Reynolds number, so therefore Nusselt's number will be equal to what? C1 into Re times C2. Okay, so what is C1? 0.035, 0.035, Re 4091.18, and C2 is 0.8. Okay, 0.035 into 4091.18 0.8. Okay, so this one you'll get 27.136. Okay, so from here now we will put in this equation. Okay, Nusselt number is equals to Hg into B divided by kg. Okay, so Nusselt number 27.136 27.136, and Hg you need to calculate. Bore is 0.089. Okay, and your kg 0.09. Okay, so from here Hg is equals to 27.136 into 0.09 divided by 0.089. So that is 27.44 watt per meter square per Kelvin. Okay, so this is your Hg. Now therefore Q convection, sorry, your Q convection will be equal to Hg into Tg minus Tw. Okay, so Hg is 27.44, and remember, difference whether you write in Kelvin or degree Celsius doesn't change. Okay, so this will be 2100 minus 190, minus 190 watt per meter square. Okay, 27.44 into 2100 minus 190, so you'll get your answer as 52.410 kilowatt per meter square. Okay, fine. So let us go to the next question then. The gases in the cylinder of an IG engine has a specific internal energy of 800 kilojoule per kg and a specific volume of 0.06 meter cube per kg at the beginning of the expansion. Okay, the expansion of the gas may be assumed to take place according to PV to the power 1.5 is equals to constant from 55 bar to 1.4 bar. The specific internal energy after the expansion is 230 kilojoule per kg, and calculate the heat rejected to the cylinder cooling water. Okay, so let us do this. Before expansion, okay, before expansion, U1 is equal to 800 kilojoule per kg. Okay, V1 is equal to 0.06 meter cube per kg. Okay, and P1 is equals to 55 bar. After expansion, okay, U2 is equal to 230 kilojoule per kg. V2 is not given, and P2 is equals to 1.4 bar. Now this expansion process takes place, PV to the power 1.5 is equals to constant. Okay, so this is the process of expansion. Okay, so you have to calculate the heat rejected. Okay, so for you have to calculate Q1 to 2. Okay, so for that, according to first law of thermodynamics, Q1 to 2 will be equal to W1 to 2 plus delta U. Okay, since these are all specific, so I will not use the capital letter here. Okay, Q1 to 2 will be equal to W1 to 2. Okay, so delta U will be equal to U2 minus U1. Okay, and we have these values. U2 is 230, U1 is 800, so this will be minus 570 kilojoule per kg. Now for this polytropic process, work done for polytropic process is equals to what? P1 V1 minus P2 V2 divided by n minus 1. Okay, so you have P1, you have V1, so your idea will be just to calculate V2. Okay, and you have also got a value of n. Okay, so P1 V1 to the power 1.5 will be equal to P2 V2 to the power 1.5. Okay, so V2 by V1 to the power 1.5 is equals to P1 divided by P2. So this implies V2 is equals to V1 into P1 by P2 to the power 1 divided by 1.5. Okay. So what is V1? 0.06. What is P1? 55. What is P2? 1.4. Okay, 1 divided by 1.5. So from here V2 is equals to 0.06 into 55 by 1.4 by 1 by 1.5. Okay, 0.6933. 0.6933 meter cube per kg. Okay, so therefore W1 to 2 will be equal to P1 V1 minus P2 V2 divided by n minus 1. So what is P1? 55 into 10 to the power 2 P1 minus V1 into V1 is 0.06. okay, minus P2 1.4 into 10 square into 0.6933 divided by 1.5 minus 1. Okay, this will also be in kilojoule per kg. Into 100.06 minus 1.4 into 100 into 0.6933 divided by 0.5. Okay, so this will be 465.876 kilojoule per kg. Now therefore Q1 to 2 is equals to W1 to 2 plus delta U. So this is 465.876 minus 570 kilojoule per kg. Okay, 570 minus 465.876, so that is minus 104.124 kilojoule per kg. Okay, so this is the change of that is the heat transfer. Okay, so let us go to the next question. An SI engine operating at 1200 rpm has 16.8 bore with a spark plug offset by 6 mm from the center. The spark plug is fired at 20 degree before TDC, and it takes 6 degree of engine rotation for combustion to develop and get into the flame propagation mode, where the average flame speed is 18 meters per second. Let the speed increase, engine speed is increased to 1600 rpm, thus swirl is increased so that the flame front VF is proportional to 0.85 times N. Consider the same delay period and the same end of combustion. Calculate how much ignition timing must be advanced. Okay, so distance is equal to b by 2 plus offset now, because in the earlier case what we have done, the offset was not there. So what is the distance? So bore is 16.8 by 2, 16.8 into 10. Basically I will do this one. Sorry, I will express everything in meter, it will be better. 16.8 divided by 2 into 100, so this will be in meter, plus 6 divided by 1000 meter. Okay, 16.8 divided by 200 plus 6 divided by 1000, so you'll get this one as 0.09 meter. 0.09 meter. Okay, and flame speed is given to you as 18 meters per second. Okay, therefore time of propagation, that is flame propagation, is equals to what? Distance divided by Vf. Distance divided by speed is equals to time, so this will be 0.09 divided by 18. So you'll get this one in seconds. Okay, 0.09 divided by 18, so this is 5 into 10 to the power minus 3 seconds. Okay, now these seconds we can express in rotation angle also. Okay, so therefore rotation angle during flame propagation is equal to what? See, one revolution 360 degree it takes. So you have the RPM, number of revolutions per second, and you have the time. Okay, so we will first calculate the what you call number of revolutions that will be completed in 5 into 10 to the power minus 3 seconds. So number of revolutions completed in 5 into 10 to the power minus seconds will be how much? It will be your 1200 RPM divided by 60. This is the number of revolutions per seconds. Okay, now you have the time, that is 5 into 10 to the power minus 3 seconds. So this goes, so you have got number of revolutions. Now one revolution is equal to 360 degree, so this many number of revolutions will be equal to this much degree. Clear? Okay, so you will get this one as 36 degree. Okay, now for the first case at 1200 RPM, okay, the spark plug is fired at 20 degree before TDC, and it takes 6 degree of engine rotation for combustion to develop and get into flame propagation mode. Flame propagation mode. Okay, therefore rotational angle will be from where? Is from, see, the spark plug is fired 30 degree before BDC and it takes 6 degrees for the combustion to develop. Okay, so that means it doesn't start from 20 degree BDC, it will basically start from 14 degree BDC before TDC, before TDC, and now the total is 36 degrees, so 14 degree, and you have to got 14 degree, and after that you have to again run for 22 degrees, so this will be from this one to 22 degree after TDC. Okay, so this is actually the rotational angle during your flame propagation time. Okay, now next case is when the speed is 1600 RPM now. Okay, now when the speed is 1600 RPM, saying that Vf is proportional to 85 times the ratio of their RPM. Okay, not ratio, sorry, RPM. Okay, that is 0.004 sorry, this is 0.85 into 1600 divided by 1200 into 18, that is equal to 20.4 meter per second. Okay, therefore time of flame propagation is equal to what? 0.09, this is the distance we have already calculated, divided by speed. Okay, that is 0.0004412 seconds. Okay, similarly, just like the previous case, therefore rotation angle during flame propagation, that is the total rotation angle, that will be equal to, once again, number of revolutions that will be completed in this time, that is 1600 divided by 60 revolutions per seconds. Okay, into 0.0004412 seconds gone, into 360, because one revolution this one. Okay, now if you do this, you will get this one as 42.35 degree. Okay, so for the same flame termination at 22 degree after TDC, they are telling us that the flame stops at the same time. Okay, that is 22 degree after TDC, flame propagation must start now earlier. Okay, because the angle is bigger now. Earlier case your angle was 36 degree, now your angle is 42.35 degree. Okay, so flame propagation starts at 20.35 degree before TDC. Okay, and spark firing starts at 26.35 degree before TDC. Okay, so therefore your ignition timing is advanced by 42.35 minus 36 degree, that is 6.35 degree. Okay, so by 6.35 degree everything will be advanced now, because your ending is the same, but your this degrees, the angle of rotation is higher. So in this case we will do this. Okay, fine. So let us go to the next question then. So to properly calculate your carbon dioxide emissions from automobiles, one must account for the carbon in the fuel that is emitted in the form of carbon monoxide and unburned hydrocarbons. So first you have to calculate the grams of the fuel that is per mile of a travel of a car that gets 16.2 miles per gallon. The density of gasoline is 739 grams per liter. Okay, volume of gasoline required for 16.2 miles is equals to 1 gallon. Okay, therefore volume of gasoline required for 1 mile, this will be 1 divided by 16.2 gallon. Okay, zero point 0.0617 gallon. Okay, now we know 1 gallon is equal to 3.79 liters. Okay, therefore volume of gasoline required for 1 mile, this will be 0.0617 into 3.79 liters. Okay, zero point 234 liters. Okay, therefore mass of gasoline required is equal to volume into density. Okay, 0.234 into 739 grams. Okay, one 72.93 gram. Okay, so you have to calculate the grams of the fuel consumed per mile. Okay, the next is molar mass of octane is equal to what? 12 into 8 plus 18 into 1, that is equals to 114 grams per mole. Okay, so in each mile, mass of gasoline required is equal to 172.93 gram. Okay, therefore in each mile, number of moles of gasoline required is equal to 172.93 divided by 104 moles. Okay, so this is 1.52 moles. Okay, 1.52 moles are required. Now number of moles of carbon in 1 mole of octane is equal to 8. Yes or no? Therefore mass of carbon in each mole of octane is equal to what? 8 into 12, that is equal to 96 gram. Okay, therefore mass of carbon in 1.52 moles, that is equal to 96 into 1.52 gram. Okay, so that is 145.92 gram. Okay, so what we are about to calculate, if the fuel composition is approximately this one, how many grams of carbon are emitted? So this much, so this is the mass of carbon emitted per mile. Okay, let us go to the next question. The exhaust emissions, combustion products are this one, these things are given to us. So all concentrations are volume on a dry basis. The engine fuel is isooctane, and you have to determine the emission index. Okay, so given carbon dioxide compositions, these are given, so I will not write this one. Okay, so emission index of NO, that will be equal to composition of NO divided by composition of carbon monoxide plus composition of CO2 into X into molecular mass of NO divided by molecular mass of C8H18. Okay, so and emission index of unburned hydrocarbon UHC, that will be equal to unburned UHC divided by CO. Okay, unburned hydrocarbons divided by molecular mass of C8H18. So we just need to know this one, XNO. What is this? 115 ppm, that is equal to 115 into 10 to the power minus 6. Okay, XCO 0.13%. Okay, and this can also be written as 0.0013. Clear? XCO2 14.7%, that is 14.7 into 10 to the power minus 3. Okay, and XUHC 613 ppm, that is 613 into 10 to the power minus 6. Again, molecular weight of nitrogen oxide is equal to what? 30 grams per mole. Okay, and C8H18 is equal to what? 114 grams per mole. Okay, unburned hydrocarbon is equal to 30 gram per mole. Now if you put all these values, you will get emission index for NO will be equal to 0.0016296 kg per kg. Okay, and emission index for unburned hydrocarbons, you'll get this one as 0.008686 kg per kg. Okay, so let us go to the last question of today's talk. A 4-stroke 4.2 liter V6 square SI engine at 2500 rpm has the spark mounted on the center line of the cylinder head. The spark is fired at 21 degree before TDC, and it takes 6 degree of crank rotation for the combustion to develop and get into the flame propagation. The average flame speed at 2500 rpm is 22.85 meter per second, and the connecting rod length is 20 centimeter. Calculate the bore of one cylinder and the mean piston speed, the time of one combustion process after the flame has developed, that is the time for the flame front to reach the wall in seconds, the crank angle when the flame propagation starts with respect to TDC, and the crank angle when the flame propagation ends with respect to TDC. Okay, so given 4.2 liter V6 square SI engine, okay, and N is 2500 rpm, spark is fired 21 degree before TDC, and it takes 6 degree of crank rotation, 6 degree of crank rotation for combustion to develop and get into flame propagation. Okay, average flame speed is equal to 22.85 meter per second. Length of connecting rod is equal to 20 centimeter. Okay, so you have to calculate bore of one cylinder and mean piston speed at 2500 rpm. Okay, so VD is equal to 4.2 by 6 liter, that is 0.7 into 10 to the power minus 3 meter cube. Okay, pi by 4 B square into S is equals to BD. This can also be written as pi by 4 into B cube is equals to VD, since it is a square engine. Okay, so from here B is equal to 4 into what is VD, 0.7 into 10 to the power minus 3 divided by pi to the power 1 by 3 meter. So you'll get this one as 0.09623 meter. Okay, and this will also be equal to S. Now therefore mean piston speed is equals to 2 into S into N. Okay, so that is 2 into 0.09623 into 2500 by 60 meter per second. Okay, 2 into 0.09623 into 2500 divided by 60, 8.019 meters per second. 8.019 meter per second. Okay, next is time for flame to reach the wall. Okay, VF is given as 22.15 meters per second. Okay, and distance is equal to B by 2, because here there is no offset, so this will be 0.09623 divided by 2 meter, that will be 0.048115 meter. Okay, so therefore time to reach the wall will be equal to what? Distance divided by Vf, and distance is 0.048115 divided by Vf is 22.15. okay, this will be 2.1 into 10 to the power minus 3 seconds. Okay, crank angle when flame propagation starts. Okay, since spark is fired 21 degree before TDC and it takes 6 degree crank rotation for combustion to develop. Okay, so the spark is fired 21 degree before TDC, but there is a gap of 6 degree. Okay, so before this 6 degree actually that flame doesn't burn. Okay, even if the spark is burned. So therefore crank angle when flame propagation starts is equal to what? 21 minus 6, that is 15 degree before TDC. Understood? So actually 15 degree before TDC only the crank propagation starts. Now next is crank angle when flame propagation ends. Okay, so that means when the flame will stop. Now rotation angle for flame propagation. So we know the flame propagation duration, that is 2.1 into 10 to the power minus 3. Okay, so 2500 divided by 60 revolutions per seconds. Okay, and the flame propagation time is basically 2.1 into 10 to the power minus 3 seconds. Okay, so that means this much revolutions is completed within this much amount of second, and in one revolution 360 degrees, so this much revolution, that will be this one into 360 degrees. So this is your crank angle that it will make. So that means 31.5 degree. Okay, so now that means what? 14 degree before TDC and after that so that means if this is the diagram, so if this is TDC, so this is 14 degree before TDC. Okay, and a total of, it will have to go a total of 31.5 degree. So with respect to TDC, so this remaining one it will get. Okay, so therefore crank angle when propagation ends is equal to what? 31.5 minus 14 degree after TDC. Okay, so that is 17.5 degree after TDC. Okay, fine, I'll wait for some time if you have any doubt. Okay, I will conclude my class today. Thank you for listening.